start with is Boyles Law. So Boyles Law states that the volume of a fixed mass of gas inversely with the pressure at constant temperature. What in the world does that mean? So what does that mean? So let's say we have a syringe, okay? And the syringe, well, what does a syringe measure? It measures volume, all right? So in that syringe, this is my drawing of a syringe, by the way. All right, so you have inside these little measurement lines here. So this is going to be 0, and this highest one is going to be 60, and the middle is going to be 30. So right now, the plunger is at the very bottom. So let's say that we move that plunger all the way to the top here. All right. And so initially, your volume is 60 milliliters, and your pressure initially is going to be 1 atmosphere. All right. Now, what I want to do is I want to push the syringe. So we're going to push the syringe down to about, let's say, right here. Okay, so now that looks like it's right around what, 20 milliliters? So the final volume is right around 20 milliliters, and then the pressure, well, we don't know what the pressure is. So now I want you to do something. I want you to think, so instead of having this syringe being opened on the end, what I want you to do is take your thumb and cover it. What will happen? So there's just air inside of the syringe right now. So say you take your thumb and you cover it and you try to push it from 60 down to 20. What do you think is going to happen to the syringe? Is it going to be real easy just to push it down to 20, or is it going to start feeling some resistance as you go down to that 20 milliliter line? And so one thing that you will, what, someone to say something? All right, so what you will feel is there will be an increase in the resistance. And so I could ask Devin, who is the strongest guy in the classroom, he bench presses 500 pounds, by the way. I asked him to push the syringe down to the very bottom where it says 0. Devin can't even do it. He would end up breaking the syringe before he could push it down to the bottom. And that's because as the volume decreases, the pressure increases. So when we talk about inverse relationships, the relationship was this here, and you can flip-flop that if you want to, but the volume changes, the pressure is going to do the opposite. And so Boyles Law is all about pressure and volume, all right? As you increase the pressure of a system, the volume is going to go down, vice versa. And so when we look at this, we have to say, okay, how can we go about figuring out the pressure of this system, the pressure that's inside of here compared to the pressure? We know the pressure is going to go up, but the question is, how high is that pressure going to be? So in order to answer that question, what we have to do is we have to have an equation. And this is where Boyles Law comes into play. P1 V1 equals P2 V2. And so we know pressure 1, we know V1 because they're right here. So it started us off at 1 atmosphere. We multiply that by 60 milliliters, and we set that equal to pressure 2 times V2. Or in this case, V2 is 20 milliliters. So in order for us to solve for P2, what we have to do is we have to divide out the 20 milliliters by the other side. and that this cancels out. So P2 is equal to, all right, so we got 60, that's divided by 20, that's going to give me 3 atmospheres. So P2 is going to be 3 atmospheres. All right, so the pressure goes up by 3 times as you push down on the syringe. There is absolutely no way that you'll ever get the syringe's plunger all the way down to 0, especially if you have your thumb covering the other side. Now, the reason why that is because it's an exponential decay. All right, so it goes down exponentially. So as we look at volume and pressure, all right, so as we look at the volume and pressure, as the volume gets lower, the pressure gets higher, and eventually gets to a point where it flattens out and it doesn't change very much. And so once you get past this point right here, this is a point of no return, because no matter how much pressure you apply, no matter, your volume is never going to change. All right, the volume is always going to stay constant because of that resistance. And so as we look, focus on that graph, you see that curve form. And so as the pressure increases, the volume of a gas decreases slightly from the initial state. So volume is inversely proportional to the pressure. I did work another problem here in the lecture notes, and it says sample of oxygen gas has a volume of 150 milliliters when its pressure is 0.947 atmospheres. What will the volume of the gas be at a pressure of 0.987 atmospheres? So what I want to do is focus. This is a conceptual problem. So if the pressure goes from 0.947 atmospheres to 0.987 atmospheres, so the pressure is going up. It's not going up by much, but it's going up. The volume should go down. The question is, how much does the volume go down? Well, that's dependent on how much the pressure changes. So in this example, we set it up where we have P1 equals P2 V2. Your V1 is 150 milliliters. Your P1 is 0.947. We don't know what volume is. That's our goal. So that's V2. It's a known. And then our P2 is 0.987. So we have P1 times V1 divided by P2. And so we end up with 144 milliliters. Now, one other detail here is significant figure. There should be a decimal place right beside of the 150 milliliter mark here. So it should be 150 decimal place. All right. And that makes a difference, because without the decimal place, this would be 2 sig figs, and that this answer would not be correct because it needs to be 2 sig figs. It would actually need to be 140 milliliters, but I want this to be 3 sig figs, so we went decimal place here. So all 3 of these numbers are 3 sig figs. So your final answer is 3 sig figs, which is what it is here. All right, so make sure you make that little correction in your notes if you're taking notes. This should be 150 decimal place. So Boyles Law basically, again, talks about pressure and volume. As the pressure goes up, the volume goes down. Any questions on Boyles Law? All right, Charles Law. All right, so Charles' law states that the volume of a fixed mass of gas at constant pressure varies directly with the temperature. So this deals with volume and temperature. As the temperature goes up, the volume goes up. It varies directly with each other. Now, if they were inverse, they would do the opposite, but they're not inverses. They vary directly with each other. So they're going to be, as one goes up, the other one goes up. Now, one detail that you got to make sure you make a note of here, most common mistake that you're going to see and possibly make is converting your Celsius into Kelvin. you should always convert your temperature into Kelvin in your gas chapter, no matter what. You should do that naturally on your own as it is, but you need to really make sure that your temperatures are in Kelvin. All right, so make sure you make a note of that right now, please. Now, the other thing is volume. You can work in milliliters, you can work in liters. You're going to see in the next lecture where we talk about the ideal gas law, and ideal gas is very specific with the units. But for here, we really need to make sure that your temperature is in Kelvin. Now, to do this, you just take your Celsius and you add 273 to that number. Now, the exact value is this, so 273.15 plus degrees Celsius. All right, so if we know that our temperature is 25 degrees Celsius in the room, and we want to calculate the temperature in Kelvin, so we take the 273.15 and add that to 25 degrees Celsius, and that gives you 298.15 Kelvin. Not degrees Kelvin, but just Kelvin. So the question is, should you use the 0.15? Yes, use the 0.15 because it's the exact number. Exact number is going to give you a better answer in the very end to begin with. Now, do not mistaken that this is going to give you it's going to change your significant figures. Your sig figs are still going to be based off the information that's given to you. So now, again, the volume and temperature are proportional to each other. So, silly question. How many of you have drove a car across a bridge, a long bridge?
How long is a long bridge?
One that lasts more than 5 seconds.
Yes.
All right. So, where was this at, Devin?
On the way to the Outer Banks, there's a bridge that lasts for probably 4 or 5 minutes. I don't know how long exactly it is, but it's a while.
All right. Now, was that bridge completely flat and smooth the whole way across?
It went up in some parts and it went down in some parts. Not significantly, but there was a definite curve to it.
No, it's not no bridge is ever smooth. They have these things that are called badunks in them. You know what a badunk is?
No, I don't think I've heard of that before.
You're driving across the bridge, you're going badunk, 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 badunk. You go across these little ridges in the bridge, and it sounds like a badunk. You know what I'm talking about now?
Yeah, I know what you're talking about.
Those are badunks. So, badunks are there because do we live in a climate where our temperature stays 70 degrees the entire year? No, we don't. We have a winter, a spring, a fall, and a summer. Our temperature changes the entire year. What happens to the concrete if there's no spacing for that temperature change to take place? Well, it would crack and fall apart. If your bridge was built in such a way to where it can't expand and contract because of the temperature change, your bridges aren't going to last very long. They're going to start to crumble and fall apart after the first couple of years being built. That's why it's important that they have those spacings, the badunks in there, because you need that to stabilize and allow for that change in temperature. And so the equation for Charles' laws, V1 divided by T1 is equal to V2 divided by T2. So again, make sure that your temperature is always going from degrees Celsius into Kelvin. Always make sure that you have your temperature in Kelvin. The volume does not matter. The volume is, you can be in milliliters, liters, whatever unit that you want to make it be in. It doesn't matter in this one. It will matter in the ideal gas law though. All right, but we'll get there next time. So, all right, now how do we go about a problem here? So let's look at an example that's in the lecture notes. Okay, so the example here says that a sample neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius if the pressure remains constant? So what we have is an initial volume and temperature. And then we have a question about asking what volume. So we're looking for V2 and the temperature is 50 degrees Celsius. Now, if you were impatient and not paying attention to the detail, and you saw 25 and 50, well, if it went up by 25, that's doubling the temperature. So you would say that that should be, twice as much. Well, the problem is that you can't say that. Well, why can't I say that, Mr. Shelton? Because you have to take into consideration your temperature has to be converted into Kelvin. So converting that into Kelvin, so you have 25 degrees Celsius, that's 298 Kelvin. And then you have 50 degrees Celsius, that's going to be what, 348 Kelvin, is that right? Yeah. Nope. I had no idea how. It's just, nope, I did something screwball in my head. All right, so that's going to be 323 Kelvin, is that right? Yeah. All right, so 323 Kelvin. All right, so you can see the temperature of the Kelvin does not double. All right, and so really, that's why you have to pay attention to that. It can make a simple mistake very quickly. So the volume is 752 to begin with. All right, so we have 752 milliliters V1 divided by 298 Kelvin, which is equal to, all right, we don't know what V2 is, divided by 323 Kelvin. Now we need to get V2 by itself, so what we're going to do is we're going to multiply 325 milliliters times this part and then multiply by 325 over here. That cancels this out. So V2, all right, so let's do this. We got 325 times 752 divided by 298. That gives me 820 milliliters for V2. So with that change in the temperature, your volume goes up basically about 70 milliliters. So now, you know this because I assume that you all understand that if you wear a ring in the wintertime, it typically fits loosely, but in the summertime, it gets to the point where it's almost hard to get off because your finger swells up. Have any of you had that problem before and have experienced it? Yeah. All right. So as we can see, the volume of a gas increased as the temperature increased. Volume is directly proportional to the temperature. So this is a graphical representation of Charles' law. As the temperature changes, the volume changes directly with it. As the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. All right, so this follows this. So it's a direct relationship. As compared to Boyles' law that we talked about earlier, Boyles' law says that the volume is inversely proportional to the pressure. So as the pressure increases, the volume decreases. So you see that exponential decay there. So you got to be careful with these two gas laws so that way you don't get them confused. So Boyles is pressure volume, Charles is temperature and volume. Now the third law that we're going to look at today is Guy-Lussac's law. And Guy-Lussac deals with pressure and temperature. And so pressure and temperature are, again, directly related to each other. So as the temperature goes up, the pressure goes up. Now, if we are sitting, let's say that you are sitting in a hot car. All right. This is a spaceship car, by the way. All right. So inside, now it's a shoe car. Put some wheels on that shoe so you can roll them down the road here. All right. Inside the car, you have the windows up. It's summertime. No air conditioning on. It's just sitting in there, hot air. So you have this soda bottle inside and you don't drink it. You leave it closed. What is the possibility of that soda bottle exploding in the middle of the dead summer? So the temperature of your car gets about, I don't know, it's 120 degrees Fahrenheit roughly to 150, I think somewhere in that range. What's that going to be? That's going to be roughly, that's going to be about 80 degrees Celsius. Would you say 80 degrees Celsius is hot or cold?
It's pretty hot.
Yeah, I'd say it's pretty hot. Have y'all ever had a can blow up in your car or a soda bottle? Y'all are just too smart, aren't you? You know better to leave it in there. We all understand the temperature increases inside of a car, the pressure is going to is going to also increase inside of the car. If you leave a balloon, this is a really good example. If you leave a balloon inside of a car, that balloon will expand to a bigger size because as the temperature goes up, the pressure increases, so it's going to get bigger. Now, what would happen to that balloon if it gets to a point where pressure is a little bit too high? It's going to blow up. And so this gas law deals with pressure and temperature. And so the law that ends up having this equation here, P1 over T1 is equal to P2 over T2. So again, P1 and P2 are your pressures that you either given or you solve for. And then T1 and T2, remember that temperature, you should always convert temperature into Kelvin, just like we did in the previous. So that's not going to change. So anytime you work with temperature and the gas laws, you should always make sure that you convert your Celsius into Kelvin. Very important detail there. All right, so if we have let's say that we have a gas can or a soda bottle, doesn't matter. So let's say the temperature of that is 25 degrees Celsius initially. So that's your T1. And your pressure initially is right around 1.5 atmospheres. So the temperature inside your car gets to being 80 degrees Celsius. And then the pressure, well, we're going to figure out what that is. Okay, so question is, if the temperature goes from 25 degrees Celsius to 80 degrees Celsius, what's the pressure going to be at whenever you are at that 80 degrees Celsius mark? So what I'm going to do here is I'm going to give you guys a few minutes. So I'll give you guys about 3 minutes here. I want you guys to calculate the pressure of this bottle at that temperature. Can y'all do that for me? All right, y'all are going to be really quiet today. All right, I'll pick on someone in just a minute, so make sure you have an answer. It's 10:37, so I'll come back at 10:40. So make sure you have an answer or attempting it. Two minutes. All right, so you got about a minute left here. All right. So I'm gonna pick on Grace here. Grace, do you have an answer? Are you able to talk with your mic, Grace, or can you chat? Or which one do you want to do? You want to tell us the answer here? What's the value of pressure two? All right, yeah, go ahead and chat. Write in the chat box what your answer is, please. So Kelvin is the temperature that you should convert to. All right, so don't use Celsius. Yeah. So what did you get for the Kelvin? All right. Yeah. So what answer did you get using the Kelvin temperature? Yep. Good. That's what I got too. So good job. How many of you got 1.7768? All right. Yeah, 1.78. Yeah.
I did.
Cool. Good. Good. Yeah. Valentina, Adria, Kinsley. All right. Jacob. Yeah, I don't know if Jacob, I know you're signed in as a guest. Are you able to chat in the chat box, Jacob? All right. Good, good. Did you convert to Kelvin, Christopher? So take 1.5 divided by 298 Kelvin, and then multiply that by, so your 80 degrees needs to be converted into Kelvin. So 80 plus 273 gives you 350. So you take your answer, which was 0.00503, multiply it by 353. That's how you get 1.78. Okay, good. Yeah, so it's simple fix, right? Yeah, you're welcome. Yeah, make a mental note of that so you don't forget that. Always convert your temperature to Kelvin. All right, so moving right along here, there is a problem here that you guys can work with. So make sure you look at that as you pay attention to notes. So the last thing I want to do here today is talk about the combined gas law, all right? So this gas law expresses the relationship between pressure, volume, and temperature. Now, what we just did in the last three gas laws is we kind of focused on just two of them. So pressure and temperature, or pressure and volume, or volume and temperature. So we looked at the three different ways that you can do that using Guy-Lussac, Charles' law, and Boyles' law. All right. So combined gas law, what they're doing is they're taking all three of these together and putting them in one unit, because not always are we going to be able to keep one of those variables constant. They're going to change. In fact, all three could change at one time. And so what you want to do is try to solve for, pressure or volume or temperature, depending on the conditions. So write down this equation, P1V1 divided by T1 is equal to P2V2 divided by T2. All right. So again, P1 V1 divided by T1 is equal to P2 V2 divided by T2. So what I'll show you here is how you can remember the individual gas laws. Okay, so circle P1 V1. So this is Boyle. All right, so that's Boyle's law, deals with pressure and volume. And then you have pressure and temperature. This is Guy-Lussac's law. And then you have volume and temperature, which is Charles' law. So that's how I remember. Okay, so when I say remember these gas laws, you had individual gas laws, you could pull them out of the combined gas law. So the combined gas law makes everything easy because it's all right there in one unit. So, I say, okay, if I'm gonna work with Boyle's law, well, look, Boyle's is P1 V1 is equal to P2 V2. Perfect. That makes it easy. You get to say, okay, I'm working with volume and temperature. Okay, whose law is that? So it's not Boyle's, that's pressure volume. It's not Guy because that's pressure and temperature. Oh, wait, so it's Charles' law. So Charles' law is V1 divided by T1 is equal to V2 divided by T2. All right. So that's what I'm saying here. Okay. I want you to understand that the combined gas law has all three gas laws combined together. That's why they call it combined gas law. And you can pull out the individual gas laws from the combined gas law. So there's no reason in you having to memorize all three of those other gas laws when they're right here. All you have to do is just understand that BGC. It's like the band Bee Gees. That's what I remember. That's how I remember this. BGC. So Bee Gees. Does that kind of make sense to y'all? I don't know if y'all are probably too young to know that band, but either
I'll
way, does that?
remember that. My
Well, I'm sorry. Yeah. If you don't know who the Bee Gees are, just go ahead and do a quick search on YouTube. I'm sure you'll find out who they are pretty quickly. Everyone, I bet, has heard at least one of their songs during your life. So, yeah. So now example here. All right. So looking at the example here. So example is a helium-filled balloon has a volume of 50 liters at 25 degrees Celsius, 1.08 atmospheres. What volume will it have at 0.855 atmospheres and 10 degrees Celsius? So two things, okay? So we can't just say, okay, if pressure goes down and volume goes down, change is going to happen. It is going to happen, but the question is, what's the change going to happen? It really depends on where the volume starts and the ending volume. So So we have 50 liters at 25 degrees. So first thing here, convert this into Kelvin. Atmosphere is fine. This is fine for liters. So we're trying to solve for volume, okay? So when I go back in here, I'll look at the equation, okay? So P1, V1 divided by T1 is equal to P2, V2 divided by T2. We're trying to solve for V2. So what I've done in the guide there is I actually went ahead and rearranged it to solve for V2. So I multiply by T2 over here. That cancels this out. And then I divided by P2. All right, so P2 is gone. So we have V2 is equal to T2 divided by P2 times P1, V1 divided by T1. Now you're given the individual parts, you just have to put them together here, all right? So the pressure was, so let's look at the first set, 50, 25, and 1.08. All right, so 50 was the volume. All right, so let's see here. So V1 was 50. I'm just going to try to put it in here. All right, and that's, I think that was liters. So, all right, so that's liters. P1 was, what is it? 1.08 atmospheres. And then dividing them by the temperature was 25, so that's 298 Kelvin. All right, so that makes sure you convert that. Now we look at T2 and P2. Okay, so T2 was 10 degrees Celsius. That's going to be 283 Kelvin. Divided by T2, which was, let's see, I've got T2 already. Let's see. Okay, now it has, what volume will it have at 0.8855 atmospheres? So 0.855 atmospheres. So the hardest part is getting everything put together, okay? So how do we go about the calculation here? Well, you can just do it in steps. I'll just do 283 divided by 0.855. Let's see, 83 divided by that gives me 330.99 and multiplied by, all right, so you got 1.08 times 50, divide that by 298, that gives me 0.1812, and then 330.99 times 0.1812, that gives me 59.975 liters. All right, and so this, I think the sig figs is going to be 3 sig figs. So that number there will be rounded to 60.0 liters. So that would be your answer there. Sometimes it's best to just go ahead and keep it simple, do the calculations separately, and then put them together like I just did. Or you could just do it all in one calculation, whichever one works easiest for you. But that's how we use it, combined gas law. And so when you look at the way I've set it up here, you know, it's going to give you the same answer. It's just I put it in a little bit easier arrangement. So, but you can see on a couple different ways, but both ways give you the 60.0 liters that's the answer in the end. So